the universe is not broken. Our understanding is simply being tested at a finer level than before. Historically, moments like this have often preceded major advances. Small discrepancies in planetary motion led to new theories of gravity. Unexpected spectral lines led to quantum mechanics. In each case, the universe was behaving consistently. It was our descriptions that needed adjustment. Whether the Hubble constant tension will lead to a similar shift remains to be seen. It may resolve quietly through improved measurements, it may point toward new physics, or it may require a combination of both. For now, the number sits uneasily between two methods, carrying implications far beyond its modest appearance. It tells us that measuring the universe is not just about accumulating data, but about ensuring that different windows onto reality truly describe the same thing. Long before there were stars to flicker, galaxies to drift apart, or supernovae to briefly light up the darkness, the universe existed in a very different state. It was hot, dense, and opaque, filled with a thick fog of particles and radiation interacting constantly. Light could not travel freely. Space, as we would recognize it, was crowded and restless. Yet from that distant era, something remains, a quiet signal that still fills the universe today, and carries with it a detailed record of how everything once behaved. This signal is known as the cosmic microwave background, often shortened to CMB. It is not a picture in the ordinary sense, and it is not light you can see with your eyes. It is a faint bath of microwave radiation that arrives from every direction, nearly uniform, almost perfectly smooth, and extraordinarily informative. The existence of this background light was predicted before it was discovered. It followed naturally from the idea that the universe had once been much hotter and denser than it is now. If that were true, then as the universe expanded and cooled, there would come a moment when matter and radiation stopped interacting constantly. At that point, light would be free to travel without being scattered. That light would continue moving through space ever since, stretched to longer wavelengths by cosmic expansion. Until today, it appears as microwaves rather than visible light. When this background radiation was finally detected, it confirmed that the universe had indeed passed through such a hot, dense phase. But confirmation was only the beginning. As instruments improved, astronomers realized that the cosmic microwave background was not perfectly uniform. Tiny variations in temperature and density were present, differences of only a few parts in 100,000. Those variations turned out to be the seeds of everything that followed. Galaxies, clusters, and large-scale structure all grew from those initial irregularities. The power of the cosmic microwave background lies in the fact that it captures the universe at a very specific moment in time. Roughly 380,000 years after the beginning of cosmic expansion, conditions changed enough for light to decouple from matter. Before that moment, photons were constantly scattered by charged particles. After it, they streamed freely. The CMB is a snapshot of that transition. Because the physics of this era is relatively simple and well understood, the patterns in the CMB can be modelled with remarkable precision. Matter, radiation, and gravity interacted in ways described by equations that have been tested extensively. By analysing the size, distribution, and amplitude of the tiny temperature fluctuations in the CMB, scientists can infer the contents of the universe and how it evolved. This includes the density of ordinary matter, the amount of dark matter, the influence of radiation, and the role of dark energy. Importantly for our story, it also includes information about the expansion rate of the universe. The cosmic microwave background does not measure the Hubble constant directly. Instead, it provides a detailed account of conditions in the early universe. From that account, scientists use a model of cosmic evolution to calculate what the expansion rate should be today. This distinction is crucial. When astronomers analyse the CMB, they are not measuring nearby galaxies or stars. They are reading a relic from a time long before any of those objects existed. The expansion rate inferred from the CMB is therefore indirect. It depends on the assumption that the model used to connect early conditions to the present is complete and correct. For many years, this approach worked exceptionally well. The model used, often referred to as the standard cosmological model, successfully explains a wide range of observations. It predicts the relative abundances of elements formed early in cosmic history. It accounts for the large-scale distribution of galaxies. It describes how structures grow over time, and when applied to the cosmic microwave background, it produces predictions that match observations with astonishing accuracy. Within this framework, the expansion rate inferred from the CMB is lower than the value measured locally using Cepheids and supernovae. The difference is not enormous, but it is persistent, and because the CMB measurements are extremely precise, the uncertainty on that inferred value is small. This is what gives the disagreement its weight. The cosmic microwave background is often described as one of the cleanest datasets in cosmology. The radiation has travelled through space largely unimpeded. It is not affected by dust in the same way visible light is. It does not depend on the complex physics of stars or explosions. It reflects conditions from a time when the universe was simpler. Because of this, many scientists place great trust in what the CMB reveals. The analysis process is intricate but conceptually clear. Temperature variations across the sky are mapped with exquisite detail. The angular size of these variations encodes information about the geometry of the universe. Their relative heights and spacing depend on how matter and radiation interacted before recombination. By fitting models to these patterns, cosmologists extract a set of parameters that describe the universe as a whole. One of those parameters is the Hubble constant, not measured directly but inferred. When this inference consistently yields a value lower than local measurements, the question becomes unavoidable. Is the model missing something? Or are the local measurements subtly biased in a way not yet understood? From the perspective of the early universe, the logic is compelling. Given the observed CMB patterns and a well-tested physical framework, the expansion rate today should have a specific value. Deviating from that value would require altering the model in some way. Such alterations are not impossible, but they are constrained. Any change must preserve the model's success in explaining everything else the CMB gets right. This is a tall order. One possibility is that additional components existed in the early universe, altering expansion before recombination. Extra forms of radiation, for example, could change how quickly the universe expanded at early times, leading to a different inferred Hubble constant today. These ideas are explored carefully, but they must fit within tight observational limits. Another possibility is that dark energy behaves differently than assumed. In the standard picture, dark energy becomes important only relatively recently. If its behaviour changed over time, it could affect the relationship between early and late expansion. Again, such changes must be subtle enough not to disrupt other observations. There is also the possibility that gravity itself behaves slightly differently on cosmic scales. Modifications to general relativity have been proposed, but they are heavily constrained by data from many sources. Each of these ideas represents a way to reconcile the CMB inferred expansion rate with local measurements. None has yet provided a fully satisfactory solution. What makes the cosmic microwave background especially intriguing in this context is its internal consistency. The same data set that implies a lower Hubble constant also matches a wide array of other observations. This coherence makes it difficult to dismiss the result as a fluke or artifact. At the same time, the CMB does not exist in isolation. Its interpretation depends on assumptions. While those assumptions are well motivated and extensively tested, they are still assumptions. If something about the universe's contents or behaviour has been overlooked, the inferred expansion rate could shift. This is the delicate balance at the heart of the current tension. On one side, local measurements tell us how the universe appears to be expanding now, based on direct observation of stars and galaxies. On the other side, the cosmic microwave background tells us how the universe behaved when it was young, and, through a model, how that behaviour should connect to the present. Both stories are internally consistent, both are supported by strong evidence. And yet, they do not quite tell the same story about how fast expansion is happening today. From a broader perspective, this is not a failure. It is a moment of opportunity. The CMB gives us a view of the universe in its infancy. Local measurements give us a view of it in maturity. If those views disagree, then the transition between them holds valuable information. It may be that the universe's expansion history includes features we do not yet fully understand. It may be that subtle physical effects become important only at certain times. Or it may be that the resolution lies in refining measurements further. It is worth emphasizing that the cosmic microwave background is not mysterious in the sense of being vague or poorly understood. It is one of the most precisely measured phenomena in science. Its patterns have been mapped, analysed and reanalyzed countless times. The disagreement it reveals is not born of ignorance, but of precision. As we sit with this idea, there is no need to resolve it immediately. The universe is under no pressure to explain itself quickly. It has left us a detailed record of its early state, written in faint microwaves that fill all of space. We are still learning how to read that record fully. At some point, comparison becomes unavoidable. Once measurements grow precise enough and methods mature enough, the numbers they produce have to be placed side by side. That moment arrived quietly in cosmology, not with an announcement, but with spreadsheets, plots, and tables that stubbornly refused to line up. On one side sat the nearby universe, distances measured step by step, from parallax to Cepheid stars to supernovae. Redshifts recorded carefully, expansion inferred directly, here and now, from objects that exist in the present cosmic neighbourhood. On the other side stood the early universe, patterns frozen into ancient radiation, decoded through well-tested physics, projected forward across billions of years to predict how fast expansion should be today. When those two approaches were first compared seriously, the expectation was simple. They might differ slightly, but as uncertainty shrank, they would converge. That is what science trains us to expect. Independent methods grounded in the same underlying reality should eventually agree. They did not. At first, the disagreement was easy to dismiss. Early measurements of the expansion rate had large error bars. Different values overlapped comfortably. Any apparent difference could be blamed on limited data or incomplete calibration. No one was alarmed. But as the years passed, the situation changed. Observations improved, telescopes became more sensitive, analysis techniques grew more sophisticated, error bars tightened. And instead of drifting toward one another, the two values began to separate. The local measurements, based on stars and supernovae, consistently pointed to a faster expansion rate. The early universe measurements, based on the cosmic microwave background and a standard cosmological model, consistently pointed to a slower one. The gap between them grew clearer, not because the numbers moved dramatically, but because confidence in each increased. This is the moment when a discrepancy turns into a tension. To understand why this was so unsettling, it helps to look carefully at how different these two methods are. They do not share the same assumptions. They do not rely on the same physical processes. They do not even observe the universe at the same stage of its life. The local method is almost stubbornly concrete. It starts nearby, with stars whose behaviour can be studied in detail. It builds outward in careful steps. Each distance is tied to a physical object that can be observed repeatedly. Redshift measurements are paired with these distances to infer expansion. The logic is straightforward, even if the execution is demanding. The early universe method, by contrast, is global and indirect. It looks at the universe when it was extremely young, long before stars or galaxies existed. It relies on a model that describes how the universe evolves from that early state to the present. Within that model, the expansion rate today is not measured, but predicted. This difference matters because it means the two methods are vulnerable to different kinds of error. If something were wrong with the local measurements, it would likely involve astrophysical complications: dust, stellar evolution, calibration issues, selection bias. These are messy, real-world problems, but they are also familiar. Astronomers know how to look for them, test for them, and correct for them. If something were wrong with the early universe inference, it would point towards something deeper. Either the model used to describe cosmic evolution is incomplete, or some physical component has been overlooked. This is not impossible, but it carries broader implications. For a long time, most researchers expected the resolution to come from the local side. That is not a criticism of the work, but a reflection of how science usually proceeds. Complex layered measurement chains are often where subtle biases hide. The early universe model, by contrast, had already survived decades of testing across many independent observations. So astronomers went looking for problems in the local ladder. They re-examined parallax measurements. They improved distance calibrations using space-based observatories. They compared Cepheids in different environments. They refined corrections for dust and crowding. They tested whether supernovae behave differently in different kinds of galaxies. Each investigation tightened the methodology. Each reduced uncertainty. And with each refinement, the local expansion rate remained stubbornly high. At the same time, researchers scrutinized the early universe side just as carefully. They checked instrument calibrations, they tested alternative data processing pipelines, they explored how sensitive the inferred expansion rate was to different assumptions within the model. The result was similar. The early universe value remained stable. This is the heart of the problem. The disagreement does not arise because one method is sloppy and the other precise. It arises because both are precise, and they disagree anyway. To put it another way, the universe seems to be telling us two different things depending on how and when we listen. When we listen to nearby stars and galaxies, the universe says it is expanding at one rate. When we listen to the faint whisper of its earliest light, it says something slightly different. Neither statement appears to be wrong on its own. This has forced cosmologists into an uncomfortable position. They must either find a hidden flaw that has eluded years of scrutiny, or accept that the standard picture of the universe may be missing a piece. It is important to stress that the difference between the two values is not enormous. We are not talking about a universe expanding twice as fast as expected or half as fast. The discrepancy is on the order of 10%. In everyday contexts, that might seem trivial. In cosmology, it is not. Modern measurements are precise enough that a 10% difference is significant. It exceeds the combined uncertainties of the methods involved. It persists across independent datasets. It refuses to average away. This persistence is what gives the tension its name. Another reason the disagreement matters is that the two methods are not redundant. They complement each other. One probes the universe as it is now. The other probes it as it was then. Together, they should form a coherent narrative of cosmic history. When they do not, the narrative becomes incomplete. There is also a psychological element to this story. Scientists are trained to distrust unexpected results. When a discrepancy appears, the first instinct is to doubt the measurement, not the theory. When repeated checks fail to find an error, the discomfort grows. The Hubble tension has now passed that threshold. It is no longer a curiosity discussed in passing. It has become a central topic in cosmology, precisely because it has not gone away. Various proposals have been put forward to explain it. Some suggest that the local universe might be slightly unusual, perhaps influenced by large-scale structures that bias measurements. If our cosmic neighbourhood were atypical, local expansion might appear faster than average. This idea has been tested using galaxy surveys and simulations. So far, it does not seem sufficient. Others suggest that the early universe might have contained additional components that affected expansion before the cosmic microwave background was released. Extra radiation, new particles, or early forms of dark energy could shift the inferred expansion rate. These ideas are intriguing, but they must fit within tight constraints imposed by other observations. There are also proposals that modify gravity itself. Small deviations from general relativity on cosmic scales could alter expansion history. Such modifications are difficult to construct without conflicting with well-tested predictions elsewhere, but they remain an active area of research. What all these ideas have in common is that they attempt to reconcile two sets of data that are individually robust. This is an important point to hold on to. The tension does not imply that cosmology is broken. It implies that cosmology has reached a level of precision where its assumptions are being tested in new ways. Historically, this is often when progress accelerates. It is also worth noting what the tension does not mean. It does not mean that expansion is illusory. It does not mean that the universe behaves erratically. It does not mean that measurements are arbitrary. The universe is expanding. That fact is beyond doubt. The question is how fast, and whether that speed has been interpreted consistently across cosmic time. From a listener's perspective, it can be reassuring to remember that disagreement in science is not a failure. It is a diagnostic. When different approaches disagree, it tells us where to look more closely. In this case, it tells us to examine the bridge between early and late cosmic history. If the universe's expansion history were perfectly smooth and fully captured by current models, the two methods should agree. If they do not, then either the bridge is incomplete, or the measurements on one side are skewed in ways we have not yet identified. Another way to frame the issue is to think about clocks. Local measurements use clocks embedded in stars and explosions, processes that unfold over millions or billions of years but can be observed directly. Early universe measurements use a cosmic clock encoded in radiation patterns, frozen at a particular moment and read through theory. Both clocks tick according to the laws of physics. If they disagree about how much time has passed, then either one clock is misread or something has altered the ticking along the way. This analogy is imperfect, but it captures the intuition. The disagreement is not about whether time passes, but about how it is counted. As the field has wrestled with this problem, the tone has remained cautious. No consensus has emerged about the correct explanation. Papers propose possibilities, test them, discard them, refine them. The process is ongoing. What has changed is that the tension is now taken seriously as a feature of the data, not a nuisance to be ignored. This seriousness has also influenced how new observations are planned. Upcoming surveys, new telescopes, and alternative measurement techniques are being designed with the explicit goal of probing this discrepancy from new angles. The hope is not just to measure the expansion rate again, but to measure it differently. Different traces, different physics, different systematics. That brings us to a natural pause in the story. We have two methods, we have two answers. We have ruled out many simple explanations. What remains is a puzzle that sits at the boundary of observation and theory. The universe has not changed its behaviour. Our descriptions of it are simply being refined to the point where subtle mismatches can no longer be smoothed over. Rather than announcing itself loudly, the problem arrived as a quiet insistence. The numbers did not clash dramatically. They did not overturn tables or invalidate decades of work overnight. They simply refused to agree, and they kept refusing, no matter how carefully they were asked. Over time, that refusal earned a name, not because it was theatrical, but because it persisted. The Hubble Tension. Calling it a tension was deliberate. In science, words matter. A crisis suggests collapse. An anomaly suggests a mistake. A tension suggests something pulled in two directions at once, stretched but not broken. That is exactly how this situation feels from within the field. Two careful, independent methods are pulling on the same underlying reality, and the stretch between them is no longer ignorable. The question that naturally follows is deceptively simple. Is this tension a whisper, a small statistical oddity that will fade as measurements improve, or is it a warning, an early sign that something fundamental is missing from our picture of the universe? To answer that, it helps to step back from the numbers themselves and think about how science usually treats disagreement. Most discrepancies die young. A new dataset appears inconsistent with previous results. Researchers recheck calibrations, correct an error, refine an assumption, and the problem dissolves. This happens so often that it is almost routine. Experienced scientists expect it. Improved. Their internal consistency strengthened. As early universe measurements improved, their internal consistency strengthened as well. The gap between them did not close, it became sharper. At this point, the tension has survived enough scrutiny that it can no longer be dismissed as a transient artifact of incomplete data. That survival alone does not guarantee profound consequences. Nature is under no obligation to reveal new physics every time we refine a measurement. Sometimes the resolution really does lie in a subtle, systematic effect that takes years to uncover. But sometimes, persistent discrepancies signal that our theoretical framework is incomplete. History offers examples of both outcomes. In some cases, anomalies vanished with better instrumentation. In others, they opened doors to entirely new ways of understanding reality. The difficulty lies in knowing which situation you are facing while you're still inside it. The Hubble tension sits squarely in that ambiguous zone. From one perspective, the disagreement is modest. A difference of several kilometers per second per megaparsec may sound dramatic, but in absolute terms it is small. The universe is still expanding. Its overall behaviour is well described. No observation suggests a catastrophic failure of cosmology. From another perspective, the disagreement strikes at the heart of the standard model of cosmology. That model rests on a delicate balance between different components: ordinary matter, dark matter, radiation, and dark energy. It has been remarkably successful in explaining a wide range of observations with a small set of parameters. The Hubble constant is one of those parameters. If that parameter cannot be made consistent across methods, then either one method is wrong in a way we do not yet understand, or the model itself needs adjustment. That is why the tension matters. One way to frame the issue is to ask where flexibility exists. The local measurements rely on astrophysical objects whose behaviour is complex but observable. Cepheids and supernovae are governed by known physics, but they exist in messy environments. Dust, crowding, and stellar evolution all introduce complications. If a hidden bias exists, it is most likely to hide here. Yet that is also where scrutiny has been most intense. The early universe inference relies on a theoretical framework that has passed many tests, but it is also more abstract. It extrapolates forward from a time when conditions were extreme and very different from today. If something unexpected happened in between, the model might not capture it. That flexibility cuts both ways. Supporters of the idea that the tension is a whisper often emphasize caution. They point out that cosmology has a long history of apparent problems resolving themselves quietly. They argue that no single discrepancy, especially one of this size, should prompt dramatic conclusions. Improved data from new instruments could still bring the numbers together. Supporters of the idea that the tension is a warning point to its persistence. They note that independent teams, using different datasets and methods, keep finding the same split. They argue that if the problem were purely observational, it would likely show more variation across analyses. Instead, the results cluster tightly around two different values. There is also an intermediate position, one that treats the tension neither as trivial nor as revolutionary, but as informative. In this view, the discrepancy is telling us something specific about the transition between early and late cosmic times. It may not require a complete overhaul of cosmology, but it may require adding nuance. For example, it is possible that the expansion history of the universe includes subtle features not captured by the simplest models. Perhaps dark energy does not behave exactly as assumed. Perhaps additional components influenced expansion briefly in the early universe and then faded away. Such scenarios would not overthrow the standard model, but they would extend it. This is why the phrase whisper or warning is so apt. A whisper suggests something faint but real, something that requires careful listening. A warning suggests attention is needed but not panic. The Hubble tension fits both interpretations depending on how one weighs the evidence. Another aspect worth considering is how the tension has shaped research priorities. It has not frozen progress or created division. Instead, it has motivated new measurements and new approaches. Astronomers are actively seeking alternative ways to measure expansion that bypass parts of the traditional distance ladder. Gravitational waves, galaxy clustering, and time delays in gravitational lensing are all being explored as independent probes. This diversity of approaches is healthy. It reduces reliance on any single method and increases the chances of identifying where the discrepancy originates. There is also a sociological dimension to the story. Cosmology is a field that has enjoyed remarkable success over the past few decades. Many of its major parameters were pinned down to high precision. The Hubble tension arrived as a reminder that precision does not guarantee completeness. That reminder has been taken seriously, but not emotionally. There is no sense of embarrassment or defensiveness. On the contrary, many researchers view the tension as an opportunity. It gives the field a concrete, testable problem to work on, one that could lead to deeper insight. It is also important to recognise what the tension does not undermine. It does not call into question the existence of dark matter or dark energy. It does not invalidate the evidence for cosmic expansion or the hot early universe. Those pillars remain solid. What it challenges is the assumption that our current description is final. From a listener's perspective, this can feel strangely reassuring. Science is often portrayed as a march towards certainty, but in reality it is a process of refinement. Moments like this, where certainty pauses and questions resurface, are part of that process. There is no shame in not knowing yet. In fact, the universe seems particularly adept at revealing its secrets gradually. It allows us to build models that work well enough to be useful, then nudges us toward improvement by exposing their limits. The Hubble tension may be one of those nudges. Another way to think about the situation is to consider scale. The early universe measurements probe conditions when the universe was extremely uniform. The local measurements probe a universe that has developed structure, complexity, and variation. It is not unreasonable to suspect that connecting those two regimes might involve subtleties. If so, the tension is not a sign of failure, but of transition. It is also worth noting that the language of whisper and warning is not meant to dramatize. It reflects uncertainty about interpretation, not fear. No matter how this resolves, the universe remains coherent. What changes is our description. As research continues, the tension may shrink. It may persist. It may even grow slightly as measurements become even more precise. Each outcome carries different implications, but none invalidate the careful work that has led us here. For now, the most honest stance is one of attentiveness. The numbers are telling us something. We do not yet know exactly what. That is not a problem to be rushed. The universe took billions of years to arrive at its current state. Understanding it may reasonably take time as well. Age is one of those ideas that feels simple until you try to pin it down precisely. For people, it is counted in birthdays and memories. For stars, it is traced through slow changes in brightness and composition. For the universe, age is inferred indirectly, stitched together from expansion rates, physical models, and the faint echoes of early conditions. When the numbers describing expansion refuse to agree, age becomes one of the first questions to wobble. If the universe is expanding faster today, then working backwards suggests it reached its current size more quickly. That points toward a younger universe. If expansion is slower, the same backward extrapolation stretches time out, implying an older cosmos. This is not a philosophical distinction. It is a mathematical consequence of how expansion connects distance, time, and scale. Under the standard picture, using early universe measurements and a slower present-day expansion rate, the universe is about 13.8 billion years old. This number is not arbitrary. It emerges from a self-consistent model that connects the cosmic microwave background, the growth of structure, and the observed abundances of light elements. Everything fits together neatly. Local measurements, however, lean toward a slightly faster expansion today. When that faster rate is folded into cosmic history, the implied age shrinks. Not dramatically, but enough to matter. The difference is on the order of several 100 million years. At first glance, that may not sound significant. Hundreds of millions of years vanish easily when talking about billions. But in cosmology, margins matter. The age of the universe must be consistent with the ages of its oldest inhabitants. Stars, globular clusters, and the chemical record of galaxies all place lower limits on how much time has passed since the universe began expanding. This is where the tension becomes tangible. Astronomers have studied some of the oldest stars in the Milky Way in exquisite detail. Their compositions, luminosities, and internal physics reveal how long they have been shining. Many of these stars are over 12 billion years old. Some estimates push close to 13 billion. These numbers already press up against the lower end of what a younger universe would allow. If the universe was significantly younger than these stars, the situation would be impossible. Stars cannot be older than the universe they formed in. While current local expansion rates do not force such a contradiction, they reduce the margin for error. An older universe, by contrast, offers more breathing room. A slower expansion rate today allows more time for stars to form, evolve, and reach the states we observe. From this perspective, the early universe value feels more comfortable. Yet comfort is not a scientific criterion. The question is not which age feels more intuitive, but which age is implied consistently by all available evidence. Right now, the evidence points in two slightly different directions, depending on how it's interpreted. One important subtlety is that age is not determined by the Hubble constant alone. The universe did not expand at a constant rate throughout its history. Early on, radiation and matter dominated, slowing expansion. Later, dark energy became important, speeding it up. The present-day expansion rate is just one piece of that story. This means that two universes with the same age could, in principle, have different present-day expansion rates if their expansion histories differ. Conversely, two universes with the same expansion rate today could have different ages if their past behaviour differed. This opens an intriguing possibility. Perhaps the universe is neither significantly younger nor older than currently thought. Perhaps its expansion history includes subtle features that alter how we connect early and late times. For example, if the universe expanded slightly faster than expected for a brief period early on, then slowed later, the present-day expansion rate inferred from early observations could differ from the local one, without dramatically altering the overall age. Such scenarios are actively explored. Another possibility is that dark energy does not behave exactly as assumed. In the simplest model, dark energy has a constant density and exerts the same influence over time, If its behaviour changed slightly, becoming more or less influential at different epochs, the expansion history would shift. Age estimates would shift with it. There is also the question of spatial curvature. The universe appears very close to flat, but even a small deviation could affect how distances and times are related. Current measurements constrain curvature tightly, but not infinitely so. Each of these possibilities offers a way to adjust age without discarding the entire framework of cosmology. Still, it is important to emphasise that no scenario currently requires a radical revision of cosmic age. We are not choosing between a universe that is 10 billion years old and one that is 20. The debate lives in the margins, but those margins matter because they test internal consistency. From a broader perspective, age is a derived quantity. It is not measured directly. It emerges from how we interpret expansion, gravity, and the contents of the universe. When those interpretations are challenged, age naturally becomes uncertain. This uncertainty is not a weakness. It reflects honesty about what is inferred and how. There is also a human tendency to treat cosmic age as a single, definitive number, when in reality it is better thought of as a range supported by different lines of evidence. That range has narrowed dramatically over the past century. The current tension nudges at its edges, but it does not blow it apart, as researchers explore whether the universe might be slightly younger or older than currently estimated. They are not rewriting the story from scratch. They are adjusting details, checking compatibility, and asking whether the same framework can accommodate all observations. One reason this matters is that age connects deeply to other cosmic milestones. The formation of the first stars, the emergence of galaxies, the build-up of heavy elements. These events have timelines inferred from observation. Any change in age must remain consistent with those timelines. So far, both the younger and older interpretations can be made consistent, but not without careful tuning. Another way to think about the question is to reverse it. Instead of asking whether the universe is younger or older, ask what kind of universe would produce the measurements we see. That shifts focus from age as a number to age as a consequence. In that framing, the tension suggests that something about the universe's expansion history is not being captured fully. Whether that missing piece affects age directly or indirectly remains open. For listeners, it may be reassuring to know that the universe's age is not suddenly up for grabs in a dramatic sense. The broad picture remains stable. What is changing is our confidence in the exact decimal places. There is also a quiet symmetry here. Early universe measurements look back to a time when the universe was simple and smooth. Local measurements look at a universe that has become complex and structured. Age is the thread that connects those two views. If that thread feels slightly stretched, it tells us to examine the weave more closely. Science rarely answers such questions by declaration. It answers them by accumulation. New data, new methods, new cross-checks. Over time, the range of possibilities narrows. As that process continues, the question of age remains a useful guide. It keeps attention on consistency. It forces models to account not just for expansion rates, but for the lived history of the universe's contents. Whether the final resolution nudges the age slightly upward, slightly downward, or leaves it largely unchanged, the exercise itself deepens understanding. It reminds us that even something as seemingly settled as the age of the universe rests on interlocking assumptions. Those assumptions are now being tested with unprecedented precision. Long after gravity had finished shaping the first galaxies and stars had settled into their slow, predictable lives, something unexpected began to matter more and more. It did not shine, it did not clump, it did not announce itself with explosions or radiation. Yet over time, it quietly took control of the universe's large-scale behaviour. Expansion, which had once been slowing under gravity's pull, began to speed up instead. The universe was not just growing, it was accelerating. This behaviour was not anticipated. For decades, cosmologists assumed that expansion, once set in motion, would gradually decelerate. Matter attracts matter. Gravity pulls things together. Even in an expanding universe, that pull should act like a brake. The more matter the universe contained, the stronger the braking effect should be. Expansion might continue forever, or it might eventually reverse, but it should slow. Observations disagreed. When astronomers used distant supernovae to trace how expansion behaved in the past, They found that the universe was expanding more slowly billions of years ago than it is today. That result was deeply counterintuitive. Instead of slowing down, expansion had been speeding up. Something was acting against gravity on the largest scales imaginable. The name given to that something was dark energy. Calling it energy was a choice of convenience, not understanding. Dark energy is not energy in the familiar sense of heat, motion, or light. It is a label for whatever is causing the expansion of the universe to accelerate. It does not describe a substance with known properties. It describes an effect. That distinction matters. Dark energy enters the equations of cosmology as a term that drives space to expand faster over time. In the simplest version of the theory, it has a constant density. As the universe expands and matter becomes more dilute, dark energy does not thin out. Its influence grows relative to everything else. Eventually, it dominates the cosmic budget. Today, dark energy accounts for roughly 70% of the total energy content of the universe. Ordinary matter, the atoms that make up stars, planets, and people, contributes only a few percent. Dark matter makes up most of the rest. This breakdown is inferred from multiple independent observations, including the cosmic microwave background, galaxy clustering, and supernova distances. In this standard picture, dark energy behaves like a constant background pressure, pushing space apart uniformly. It does not vary from place to place. It does not interact with matter in any detectable way, other than through gravity. It simply exists, quietly shaping the fate of the cosmos. This model has been remarkably successful. It explains why expansion accelerates. It fits the patterns seen in the cosmic microwave background. It matches the observed distribution of galaxies. For many years it appeared sufficient. Then the Hubble tension sharpened. If dark energy behaves exactly as assumed, then the expansion history inferred from the early universe should connect smoothly to the expansion measured locally today. The fact that it does not raises a natural question. Could dark energy be doing something more subtle? One possibility is that dark energy is not constant. Perhaps its influence has changed over time. If dark energy was slightly stronger or weaker in the past than it is now, the expansion history would shift. Early universe observations would infer one present-day expansion rate, while local measurements would reflect another. This idea is often described as evolving dark energy. In such models, dark energy might have been less influential in the early universe and grown stronger later, or it might have behaved differently during certain epochs. Even small deviations from constancy could have noticeable effects when extrapolated over billions of years. Importantly, these deviations would not necessarily disrupt other successful predictions. They could be subtle enough to escape detection in most observations, while still affecting the inferred Hubble constant. This makes evolving dark energy an attractive candidate for resolving the tension. However, attraction does not equal confirmation. Any modification to dark energy must satisfy strict constraints. It must preserve the excellent agreement between theory and observation in many other areas. It must not spoil the detailed patterns seen in the cosmic microwave background. It must remain consistent with how galaxies cluster and how structures grow. Designing such models is possible, but difficult. Many proposed versions of evolving dark energy have been ruled out as data improve. Others remain viable but unproven. Another idea is that dark energy might interact with other components of the universe, such as dark matter. In the standard picture, these components evolve independently. If they exchange energy or influence each other's behavior, the expansion history could change. Such interactions would be extremely weak, otherwise they would have been detected already. But even weak interactions acting over cosmic timescales could matter. This line of thinking opens the door to new physics, but it also complicates the theoretical landscape. Introducing interactions adds parameters. Each parameter must be constrained. The risk is creating models that fit one problem but fail elsewhere. There is also a more radical possibility. Perhaps dark energy is not a separate component at all, but a manifestation of how gravity behaves on large scales. In this view, what we call dark energy emerges from modifications to gravity itself, rather than from a new substance filling space. Modified gravity theories attempt to explain cosmic acceleration without invoking dark energy as a separate entity. Instead, they alter the rules governing how space and time respond to matter and energy. These theories are mathematically rich and conceptually appealing to some. They offer a unified explanation for expansion behavior, but they face serious challenges. Gravity has been tested extensively in many regimes, from the solar system to binary stars to gravitational waves. Any modification must agree with all of those tests. So far, no modified gravity theory has clearly outperformed dark energy models across the full range of observations. Still, the Hubble tension has renewed interest in these ideas. When a simple model struggles, exploring alternatives becomes worthwhile. There is also a less dramatic interpretation worth considering. Dark energy may be exactly what the standard model says it is, but its effects on expansion may be slightly misinterpreted when connecting early and late times. The issue may lie not in dark energy itself, but in how its influence is folded into models. This could involve subtle correlations between parameters or overlooked degeneracies in data analysis. In such cases, the tension might be resolved through improved modelling rather than new physics. What makes dark energy particularly relevant to the current discussion is timing. Dark energy becomes dominant relatively late in cosmic history. The cosmic microwave background captures the universe before dark energy mattered much. Local measurements capture the universe when dark energy dominates. If something about dark energy is misunderstood, the mismatch would appear exactly where it does, between early and late measurements. This alignment is suggestive, though not conclusive. It is also worth remembering how strange dark energy already is. Even in the standard picture, it raises deep questions. Why does it have the value it does? Why did it become dominant when it did? Why does its density appear so small compared to naive theoretical expectations? The Hubble tension does not create these questions. It adds urgency to them. From a listener's point of view, it can help to frame dark energy not as a mysterious force lurking ominously, but as a placeholder for incomplete understanding. It is a name we give to observed behaviour while we work toward a deeper explanation. In that sense, dark energy has always been provisional. Whether the resolution of the Hubble tension involves modifying dark energy, adding new components, or refining measurements, the concept itself remains central. Expansion is accelerating. Something is driving that acceleration. Understanding it fully is one of the major goals of modern cosmology. The current tension suggests that understanding may not yet be complete. That is not a cause for alarm. It is an invitation. Science advances not by clinging to comfortable models, but by testing them against increasingly precise data. When models strain, they either adapt or give way to better ones. Dark energy, as currently conceived, may survive this process intact, or it may evolve into something richer. Either outcome deepens knowledge. Speculation usually enters science only after restraint has done all it can. When measurements disagree, the first response is to question technique, calibration, and assumption. Only after those avenues are exhausted does a more unsettling possibility come into view. Perhaps the framework itself is incomplete. Perhaps the laws we rely on are accurate within familiar limits, yet subtly altered when stretched across the full scale of the universe. This is where discussions move beyond refinement and into extension. Not rejection of what works, but exploration of what might be missing. Einstein's theory of general relativity has passed every direct test thrown at it, with remarkable success. It explains planetary orbits, gravitational lensing, black holes, gravitational waves, and the large-scale behaviour of space-time with extraordinary accuracy. For over a century, it has been the backbone of cosmology. Yet even Einstein understood that no theory should be considered final. Every theory has a domain of validity, and beyond that domain, new behaviour may emerge. The Hubble tension has reopened a question that many assumed was settled. Does general relativity describe gravity perfectly on the largest possible scales? Or does it require modification when applied to the universe as a whole? This is not a new idea, but it has gained renewed attention. General relativity tells us how space and time respond to matter and energy. In cosmology, it is applied under assumptions of large-scale smoothness and uniformity. Those assumptions are well supported by observation. On average, the universe looks the same in every direction and location when viewed on sufficiently large scales. Within that framework, the equations predict how expansion should evolve given the universe's contents. When early universe observations are interpreted through these equations, they imply a specific present-day expansion rate. The fact that local measurements disagree suggests that either something is missing from the contents, or the equations themselves need adjustment. One class of ideas focuses on modifying gravity directly. In these models, general relativity remains an excellent approximation in familiar environments like the solar system or galaxies, but deviates slightly on cosmic scales. The deviations are designed to be small, subtle, and difficult to detect except through precise cosmological measurements. Such theories are not arbitrary. They're constructed carefully to preserve known successes while altering behaviour where constraints are weaker. Some modifications involve adding extra fields that interact with gravity. These fields can change how space-time responds to matter over large distances without affecting local physics. Others alter the way curvature and energy relate to one another, effectively changing how expansion responds to the universe's contents. A key challenge for all such theories is consistency. Gravity is tested not just by cosmology, but by gravitational waves, binary pulsars, lensing observations, and the motion of galaxies. Any modification must satisfy all these constraints simultaneously. This is an unforgiving requirement. As a result, many proposed modifications fail quickly. They produce predictions that conflict with well-established observations. Others survive initial tests but struggle under more detailed scrutiny. A few remain viable, but none has emerged as a clear replacement for general relativity. Another direction involves introducing new components to the universe, rather than modifying gravity itself. One example is additional forms of energy or particles that existed primarily in the early universe. These components would affect expansion during that era, and then fade away, leaving little trace today. Their influence could shift the inferred expansion rate without altering late-time behaviour dramatically. Such ideas include additional relativistic particles, sometimes described as dark radiation. These particles would increase the expansion rate early on, changing how the universe evolved before the cosmic microwave background was released. When early universe data are analysed without accounting for them, the inferred present-day expansion rate could be biased. The appeal of this idea lies in its subtlety. The new components do not need to dominate or persist. They only need to exist long enough to leave a measurable imprint. However, these models face tight constraints. The cosmic microwave background is extremely sensitive to the amount of radiation present in the early universe. Adding even a small amount must be done carefully to avoid spoiling the excellent agreement with observed patterns. Another class of exotic possibilities involves interactions between known components. In the standard model of cosmology, dark matter and dark energy evolve independently. Dark matter clumps under gravity. Dark energy drives expansion. They do not exchange energy or influence each other directly. This assumption is made for simplicity, not because it is guaranteed. If dark matter and dark energy interact weakly, the expansion history could change in subtle ways. Energy transfer between components could alter how quickly structures grow and how expansion accelerates. Over billions of years, even a weak interaction could have noticeable effects. These interactions would be extremely difficult to detect directly. Dark matter already interacts very weakly with ordinary matter. Adding another weak interaction does not violate existing constraints easily. Yet modelling such interactions introduces complexity and uncertainty. As with modified gravity, the challenge is not imagining possibilities, but narrowing them down. There are also proposals that revisit the nature of space-time itself. Some theoretical frameworks suggest that space-time may have additional dimensions beyond the familiar three of space and one of time. In such models, gravity can leak into extra dimensions on large scales, altering expansion behaviour without affecting local physics. These ideas arise naturally in certain attempts to unify gravity with quantum mechanics. While fascinating, these models are speculative and difficult to test. Their predictions often depend on parameters that are not well constrained. Still, the Hubble tension has encouraged renewed interest in whether extra-dimensional effects could play a role. Another avenue involves questioning assumptions about cosmic homogeneity. While the universe is remarkably uniform on large scales, it is not perfectly so. Structures like voids, filaments, and clusters create regions with different densities. Some researchers have explored whether large-scale inhomogeneities could bias local expansion measurements. In extreme versions of this idea, a local region might be underdense or overdense in a way that affects how expansion appears locally compared to the global average. This could create an apparent discrepancy without requiring new physics. However, extensive surveys suggest that while local variations exist, they are unlikely to be large enough to explain the full tension. The universe appears too homogeneous on the relevant scales. What makes all these exotic possibilities difficult is not imagination, but discipline. Theoretical physics offers many ways to alter equations or add components. The challenge is finding ideas that are both mathematically consistent and observationally viable. This is why progress in this area is slow. It is also why caution is essential. History includes many cases where apparent anomalies inspired elaborate theories, only to dissolve with better data. Scientists working on the Hubble tension are acutely aware of this. At the same time, history also includes cases where anomalies pointed the way to profound advances. Mercury's orbit led to general relativity. Black body radiation led to quantum mechanics. In both cases, existing theories worked well until they didn't, and the discrepancies were small but persistent. The Hubble tension shares some features with those episodes, but it is too early to know whether it belongs in the same category. One important difference is that the current framework already includes elements that were once considered exotic. Dark matter and dark energy themselves were introduced to explain discrepancies. The standard model of cosmology is already an extended theory, built to accommodate observations. This raises a philosophical question. How much extension is reasonable before a framework becomes unwieldy? There is no simple answer. Science does not impose aesthetic limits, it follows evidence. If resolving the tension requires adding a new component, modifying gravity or refining assumptions, that path will be taken. What matters is that proposals are testable. Many of the exotic possibilities discussed are not vague speculations. They make predictions about other observables. They affect structure formation, gravitational lensing, or the growth of cosmic perturbations. As new data arrive, these predictions can be checked. This is where future observations become critical. Upcoming surveys and instruments will measure the universe in new ways, and with unprecedented precision. They will probe expansion using techniques that bypass traditional distance ladders. They will map structure growth across cosmic time. They will test gravity on scales never before accessible. If exotic physics is at play, it will leave traces. If it is not, those traces will be absent, and attention will return to more conventional explanations. From a listener's perspective, it is worth emphasizing that none of these ideas represent a rejection of Einstein in the everyday sense. General relativity remains extraordinarily successful where it has been tested. Even if modifications are needed on cosmic scales, they would likely reduce to Einstein's equations in familiar regimes. In that sense, new physics would extend Einstein rather than replace him. There is also a tendency to imagine new physics as something dramatic or unsettling. In practice, it is often incremental. Small terms added to equations, slight changes in behaviour under specific conditions, subtle effects that become visible only when measurements are precise enough. The Hubble tension exists because measurements have reached that level of precision. It has exposed a seam in our understanding, not a fracture. As research continues, the field remains balanced between openness and skepticism. Exotic possibilities are explored seriously, but not embraced prematurely. Conventional explanations are scrutinized thoroughly, but not assumed sufficient. This balance is not indecision, it is method. The universe does not rush, and neither does understanding. Whether the resolution involves new physics beyond Einstein or a quieter correction within the existing frameworks, the process itself is revealing. It shows how far cosmology has come, and how carefully it now listens when the universe answers back slightly differently than expected. Before leaping too far into new physics, there is a quieter, more methodical question that insists on being asked. Have we misunderstood our own tools? When two careful measurements disagree, it is not reckless to imagine exotic explanations, but it is responsible to exhaust the ordinary ones first. In cosmology, that means returning to the instruments, the assumptions, and the subtle biases that can quietly shape results without announcing themselves. Systematic errors are not mistakes in the everyday sense. They are not typos or misreadings that vanish when corrected. They are biases built into methods, instruments, or interpretations that consistently nudge results in one direction. Because they act steadily rather than randomly, they do not average out with more data. In fact, they can become more convincing as precision improves. This is why systematic errors are so difficult to detect. In the context of the Hubble tension, the possibility of a misread cosmic ruler has been taken extremely seriously. Researchers have devoted years to asking whether local measurements might be skewed by effects that are subtle enough to survive multiple checks, yet strong enough to shift the inferred expansion rate. The local distance ladder is an intricate construction. It begins with parallax measurements of nearby stars, moves through Cepheid variables, and extends outward using supernovae. Each step is grounded in physical reasoning, but each step also introduces opportunities for bias. Parallax, while conceptually simple, is limited by instrumentation. Measuring tiny angular shifts requires exquisite precision. Space-based observatories have improved this dramatically, but even small calibration offsets can propagate upward. A tiny systematic error in parallax distances could slightly miscalibrate Cepheid brightness, which in turn would affect supernova distances. This possibility has been examined carefully. Independent parallax data sets have been compared. Calibration strategies have been revised. Cross-checks with alternative geometric methods have been performed where possible. While refinements have occurred, they have not shifted the expansion rate enough to resolve the tension. Cepheid measurements themselves present another potential source of systematics. These stars often live in crowded regions of galaxies, surrounded by other stars whose light can blend with theirs. This blending can make Cepheids appear brighter than they truly are, leading to underestimated distances. Astronomers correct for this effect using high-resolution imaging and statistical modelling. Observations in infrared wavelengths reduce crowding and dust effects. Cepheids in different environments are compared. While blending remains a concern, its magnitude appears too small to account for the discrepancy on its own. Dust is another perennial suspect. Interstellar dust absorbs and scatters light, making objects appear dimmer and redder. If dust corrections are imperfect, distances can be misestimated. This issue affects both Cepheids and supernovae. To address it, astronomers observe in multiple wavelengths and model how dust alters light across the spectrum. Again, corrections have been refined repeatedly. Different teams using different dust models arrive at similar expansion rates. This consistency argues against dust as the dominant culprit. Supernovae introduce their own complexities. Type 1 supernovae are standardized using correlations between brightness and light curve shape. These correlations are empirical, not derived from first principles. If they evolved subtly over cosmic time, distances inferred for distant supernovae could be biased. This possibility has been studied extensively. Supernovae in different host galaxies are compared. Environmental dependencies are examined. Nearby and distant samples are cross-checked. While small variations exist, they do not appear sufficient to explain the full difference in expansion rates. Selection effects are also scrutinized. Astronomers do not observe all supernovae equally. Brighter ones are easier to detect, especially at large distances. If detection thresholds bias samples toward intrinsically brighter events, distances could be underestimated. Statistical methods account for this bias, but no method is perfect. Multiple independent analyses, however, yield similar results. This suggests that selection effects are not driving the tension. Another class of potential systematics involves redshift measurements themselves. Redshift is usually extremely reliable, but local motions can complicate interpretation. Galaxies do not move solely with cosmic expansion. They also have peculiar velocities due to gravitational interactions. These motions can add or subtract from redshift, especially in the nearby universe. Astronomers correct for this by averaging over many galaxies and modelling large-scale flows. While peculiar velocities add scatter, they are unlikely to produce a coherent shift in the expansion rate. On the early universe side, systematic errors are also considered carefully. The cosmic microwave background is measured with extraordinary precision, but its interpretation depends on complex data processing. Instrument calibration, foreground subtraction, and statistical modelling all matter. Independent experiments using different instruments and analysis pipelines have been compared. Their results are consistent. Foreground contamination from our own galaxy is modelled and removed. Multiple frequency channels are used to separate cosmic signal from local emission. The remaining uncertainties are small. Crucially, the inferred expansion rate from early universe data is not a direct measurement, it is a model-dependent inference. This raises the question of whether assumptions built into the model could act like systematics. For example, assuming a specific number of particle species or a specific form of dark energy constrains how expansion evolves. If those assumptions are slightly wrong, the inferred Hubble constant could shift. This is where the line between systematic error and new physics becomes blurred. Adjusting assumptions may be equivalent to introducing new components. The distinction is not always clear. What has made the systematic error explanation increasingly uncomfortable is the way different methods agree internally but disagree externally. Local measurements agree with other local measurements. Early universe inferences agree with other early universe inferences. If systematics were dominating, more internal disagreement might be expected. This does not rule out systematics, but it narrows where they could hide. One intriguing idea is that multiple small systematics could align in the same direction. No single effect would be large enough to explain the tension, but together they might add up. This is possible, though it requires an unfortunate coincidence. Scientists do not dismiss this possibility. They quantify it. They ask how large each systematic would need to be, and whether such values are plausible given existing constraints. So far, the answer has been that such coincidences are possible but increasingly unlikely. There is also the question of confirmation bias. When a result becomes well known, researchers may unconsciously make analysis choices that align with expectations. This is why blind analyses and independent teams are so important. In the case of the Hubble tension, multiple groups using different methods and philosophies have reached similar conclusions. That diversity reduces the likelihood that a shared bias is driving the result. None of this means that systematic errors have been ruled out definitively. Science rarely rules anything out completely. It does mean that simple explanations have been tested thoroughly and found wanting. This is an uncomfortable position, but also a productive one. It forces researchers to sharpen their tools, improve transparency, and design new measurements that bypass known systematics entirely. Instead of refining the same ruler endlessly, they seek new rulers altogether. Gravitational lensing time delays, for example, measure expansion without relying on standard candles. Gravitational waves from merging neutron stars offer another independent route. Large-scale structure provides still another. Each of these methods comes with its own systematics, but they are different ones. Agreement across such diverse approaches would be powerful. Disagreement would be equally informative. From a broader perspective, the intense focus on systematic errors reflects a healthy scientific culture. Extraordinary claims require extraordinary care. Before embracing new physics, researchers are making sure they have not simply misread the universe using familiar tools. That care takes time. As listeners, it may be helpful to think of this stage as calibration of understanding rather than indecision. The universe is not ambiguous. Our interpretations are being refined to match its clarity. Whether the tension ultimately resolves through identifying a hidden systematic or through extending theory, the process is the same. Measure carefully, question assumptions, compare independent approaches. At present, the balance of evidence suggests that systematics alone are unlikely to fully explain the discrepancy. But unlikely is not impossible. As new methods mature and new data arrive, the role of systematics will become clearer. Some explanations will be eliminated, others will gain support. The cosmic ruler will either be confirmed or revised. And as that unfolds, attention naturally turns toward the tools of the future. If current instruments have reached their limits, what happens when sharper eyes and different techniques are brought to bear on the same question? Into this long-running debate stepped a telescope built not to settle arguments, but to see more clearly than anything before it. Its purpose was not to confirm one number or another, but to sharpen vision, to remove layers of uncertainty that had accumulated simply because earlier instruments could not see faint details well enough. Precision, after all, often changes the kinds of questions that can be asked. The James Webb Space Telescope was conceived as a successor in capability rather than a replacement in spirit. Where earlier space telescopes excelled in visible and ultraviolet light, Webb was designed to work primarily in the infrared. This choice was not aesthetic, it was practical. Much of the universe's most important information is hidden in wavelengths that visible light telescopes struggle to access. especially when dust, distance, or cosmic redshift push signals out of reach. Infrared vision matters enormously for measuring cosmic distances. Cepheid stars, for example, shine more steadily in infrared light than in visible light. Their brightness variations become cleaner. The effects of interstellar dust diminish. Crowding from neighbouring stars becomes easier to disentangle. All of these factors reduce systematic uncertainty. Webb's resolution and sensitivity allow astronomers to isolate Cepheids in distant galaxies with unprecedented clarity, even in regions that were previously too cluttered or too faint. This improvement alone has significant consequences. When Cepheids are measured more precisely, the calibration of the entire distance ladder tightens. That calibration flows upward to supernova distances, and from there to the inferred expansion rate. Webb does not introduce a new method so much as refine an existing one to a degree that was not previously possible. Another advantage lies in Webb's stability. Operating far from Earth, shielded from heat and stray light, the telescope maintains a remarkably consistent observational environment. This stability reduces subtle instrumental variations that can introduce bias. Measurements taken months or years apart can be compared with confidence that the instrument itself has not changed in meaningful ways. For a problem as delicate as the Hubble tension, this kind of stability is invaluable. Webb's role is not limited to Cepheids. It also observes the environments in which Type 1 supernovae occur. Understanding those environments better helps refine corrections applied to supernova brightness. Host galaxy properties, local stellar populations, and dust distributions can all be studied in greater detail. These refinements matter because supernovae are not abstract points of light. They occur in real galaxies with complex histories. Subtle environmental effects, once invisible, can now be examined directly. Importantly, Webb does not operate in isolation. Its measurements are compared against those from other telescopes, both space-based and ground-based. Agreement across instruments strengthens confidence. Disagreement highlights areas needing further scrutiny. Early results from Webb have been closely watched for signs that the local expansion rate might shift. If earlier measurements were biased by unresolved systematics, sharper data might pull the value downward, closer to the early universe prediction. So far, that has not happened. Instead, Webb's measurements of Cepheids appear consistent with previous results, but with smaller uncertainties. In other words, the picture has become sharper without changing its basic outline. The local expansion rate remains high. This outcome is not dramatic, but it is significant. Sharper measurements, reducing uncertainty without altering the central value, suggest that earlier results were not dominated by gross error. The cosmic ruler, at least in the nearby universe, appears to have been read correctly. That does not mean Webb has spoken the final word. It means it has narrowed the space in which certain explanations can hide. Webb also contributes indirectly by observing very distant galaxies and early star formation. While it is not designed to measure the cosmic microwave background, its observations inform models of how galaxies evolve, how stars form, and how structures grow. These processes connect local measurements to early universe predictions. Better understanding of galaxy evolution helps refine assumptions used in interpreting both local and early data. If subtle evolutionary effects influence distance indicators, Webb is well positioned to reveal them. There is also the matter of consistency across cosmic time. One lingering concern in cosmology has been whether objects used as distance indicators behave the same way at different epochs. Cepheids and supernovae observed billions of years ago might differ subtly from those nearby due to differences in chemical composition or environment. Webb's ability to observe these objects across a wider range of distances and conditions allows those questions to be tested directly. Again, the early indications are reassuring. No dramatic evolution has been detected that would undermine their use as standard candles. This does not eliminate all uncertainty, but it reduces plausible room for large unaccounted-for effects. Another contribution of Webb lies in calibration itself. Parallax measurements from astrometric missions anchor the distance ladder at its base. Webb does not measure parallax directly in the same way, but it helps cross-check calibrations by observing objects whose distances are known through other means. Agreement across methods strengthens the entire structure. This cross-validation is crucial. The distance ladder is not a single chain, but a network. Webb adds new connections, making the network more resilient. From a broader perspective, Webb exemplifies how progress in cosmology often comes not from revolutionary ideas alone, but from incremental improvements in measurement, sharper images, cleaner spectra, better control of systematics. Each improvement reduces ambiguity. In the context of the Hubble tension, Webb's contribution has been sobering rather than sensational. It has not erased the discrepancy. It has not revealed a hidden error that explains everything away. Instead, it has confirmed that the disagreement persists even when observations are sharpened, that persistence matters. It shifts the burden of explanation. If local measurements remain robust under increasingly precise scrutiny, attention naturally turns elsewhere. Either the early universe inference must be reconsidered, or the connection between early and late times must be revised. This does not mean that Webb has solved the problem. It has clarified the landscape. Future observations with Webb will continue to refine measurements, larger samples, different environments, improve statistical power. Each dataset will tighten constraints further. At the same time, Webb's results feed into planning for other missions. Its findings inform where uncertainty remains and where new approaches might be most valuable. It is also important to recognize the limits of Webb's role. No single telescope can resolve a discrepancy that sits at the intersection of multiple methods and epochs. Webb is one piece of a larger effort, not a standalone arbiter. Still, that piece is an important one. The narrative arc here is subtle. Webb does not overturn previous work. It reinforces it with greater clarity. That reinforcement does not make the tension disappear. It makes it harder to ignore. For listeners, this can be framed as a sign of maturity rather than crisis. Cosmology has reached a point where tools are precise enough to test their own foundations. Webb represents the cutting edge of that precision. It also represents patience. The telescope was designed decades ago, built carefully, tested relentlessly, and deployed with extraordinary care. Its observations unfold slowly, methodically, each one adding a small piece to a much larger picture. That pace matches the nature of the problem. The Hubble tension is not a puzzle that yields to a single insight. It is a mismatch revealed only through accumulation. As Webb continues to observe, its role will evolve. It may not provide a direct answer to why the expansion rates differ, but it will constrain explanations more tightly. Some ideas will become untenable, others will gain plausibility. In science, narrowing possibilities is progress. As the space of uncertainty shrinks, attention turns increasingly to what remains viable. If sharper measurements continue to support the local expansion rate, then explanations that rely on local error become less attractive. The focus shifts toward global explanations. That shift does not happen abruptly. It happens through many careful studies, each one adding weight. Webb's contribution so far suggests that the local universe is being measured correctly, at least within current understanding. If that holds, then the universe may indeed be telling us that its expansion history is more complex than our simplest models assume. Suppose for a moment that the disagreement remains, not because we have failed to measure carefully enough, and not because some overlooked bias eventually reveals itself, but because the universe is genuinely doing something that our current description does not fully capture. If the numbers truly do not match, then the question shifts from how we measure to what we believe. This is where consequences begin to unfold. The first thing that would change is not a single equation or parameter, but confidence in the completeness of the standard cosmological model. That model has been extraordinarily successful. It explains a vast range of observations with a relatively small set of ingredients. It describes how the universe expanded, cooled, formed structure, and arrived at its present state. Yet success does not guarantee finality. If the Hubble tension reflects real physics rather than measurement error, then the standard model is not wrong so much as unfinished. In that case, the disagreement becomes a boundary marker. It tells us where the current framework stops being sufficient. One immediate implication would be that the expansion history of the universe is more nuanced than assumed. Right now, the model treats the transition from early to late times as smooth and well described by known components. If the present-day expansion rate inferred locally differs from the one inferred from early conditions, then something altered that transition. That alteration does not need to be dramatic. It could involve a brief episode early on when expansion behaved differently. It could involve a gradual change in how dark energy influences space. It could involve interactions that subtly reshaped cosmic evolution over billions of years. Any of these would require revising how we connect the early universe to the one we observe today. Another change would involve how cosmologists interpret precision. For decades, tightening error bars was seen as a path toward convergence. More data meant fewer disagreements. The Hubble Tension challenges that expectation. It shows that precision can sometimes sharpen disagreement rather than erase it. This does not undermine the value of precision. It reframes its purpose. Precision becomes a tool not just for confirming models, but for exposing their limits. That shift affects how future experiments are designed. Instead of merely repeating existing measurements with greater accuracy, emphasis moves toward independent methods that probe the same quantity through different physics. Agreement across such methods would reinforce confidence. Persistent disagreement would strengthen the case for new interpretation. Another implication concerns how cosmology balances observation and theory. If the numbers do not match, theory cannot simply be adjusted freely to accommodate them. Any modification must preserve the model's many successes. This creates tension of its own. Changes must be surgical, not sweeping. This is why many proposed solutions focus on narrow windows of cosmic time or subtle effects. The universe cannot be changed wholesale without breaking other things that already work. In practical terms, this means cosmologists would need to introduce new parameters cautiously. Each new parameter increases explanatory flexibility, but reduces predictive power. Too many adjustments, and the model risks becoming descriptive rather than explanatory. This balance is delicate. There is also an implication for how cosmic age is discussed. If expansion history is revised, age estimates may shift slightly. That would ripple into discussions of early star formation, galaxy assembly, and the timing of cosmic milestones. These shifts would likely be modest, but they would require re-evaluating timelines that are currently taken as settled. Similarly, the inferred size of the observable universe could change subtly. Horizons depend on expansion history. A different expansion path alters how far light has travelled and what regions are causally connected. Again, these changes would not rewrite the universe dramatically, but they would adjust our sense of scale. Perhaps the most profound change would be philosophical rather than numerical. The standard model of cosmology achieved something rare in science. It provided a unified narrative that connected the earliest observable moments to the present day with remarkable coherence. If the Hubble tension persists, that narrative develops a seam. Seams are not failures. They are places where fabric can be extended. Accepting that the model is incomplete does not mean abandoning it. It means treating it as an approximation that works extremely well within known bounds, but not perfectly everywhere. Physics has lived with this before. Newtonian gravity remains useful despite being superseded by general relativity. Classical mechanics remains valid despite quantum mechanics redefining fundamentals. Each framework continues to function within its domain. Cosmology may be approaching a similar transition. If so, the change will not arrive as a sudden overthrow. It will arrive as addition, an extension that explains why two careful measurements tell slightly different stories about the same universe. Another implication lies in how dark components are conceptualized. Dark matter and dark energy are already placeholders for incomplete understanding. If resolving the Hubble tension requires modifying their behavior or introducing new forms of energy, it reinforces the idea that the universe contains ingredients we have not yet fully characterized. This is not a sign of failure. It is a sign that observation is outpacing explanation. It is also worth considering what would not change. The universe would still be expanding, galaxies would still recede, the cosmic microwave background would still reflect a hot, dense past. The evidence for dark matter would remain overwhelming. None of that is in question. What changes is the fine structure of understanding, not the foundation. From a practical standpoint, accepting that the numbers truly do not match would influence research priorities for decades. Resources would be directed toward probing the expansion history in new ways. Alternative theories would receive more attention. Data analysis would emphasize cross-method comparison even more strongly. Educational narratives would adapt as well. Instead of presenting the Hubble constant as a settled value with minor uncertainty, It would be presented as an actively investigated quantity with multiple operational definitions. That shift would not confuse students. It would reflect reality. There is also a cultural implication within science. Moments like this test how comfortable a field is with ambiguity. Cosmology, for much of its recent history, has enjoyed convergence. Parameters narrowed, models solidified. The Hubble tension reintroduces open-endedness. How that open-endedness is handled matters. If it is treated defensively, progress slows. If it is treated as an opportunity, progress accelerates. So far, the responses lean toward the latter. Researchers debate vigorously but productively. Competing ideas are proposed and tested. No single explanation has hardened into dogma. This is healthy. Another consequence involves time itself as a concept. Expansion rate links space and time intimately. If expansion history is revised, our understanding of cosmic time gains nuance. Time since the early universe may not map as simply onto present observations as assumed. This does not make time subjective or mysterious. It makes its measurement more context-dependent. Finally, there is the question of resolution. If the numbers truly do not match, resolution will not come from declaring a winner between methods. It will come from understanding why both are right within their own contexts. That understanding may reveal that the question, how fast is the universe expanding, has more than one meaningful answer, depending on how and when it is asked. This would be a subtle but important shift. Instead of a single expansion rate characterizing the universe universally, expansion might need to be described in a way that reflects its history more explicitly. Such a shift would not make cosmology less precise. It would make it more accurate. It can be reassuring to remember that science is not a quest for final answers, but for better questions. The Hubble tension may be forcing cosmology to ask a better question about expansion than it has before. Rather than asking for one number to rule them all, it may need to ask how expansion behaves across time and scale, and how different measurements illuminate different aspects of that behaviour. If that is the case, then the disagreement is not a problem to be solved away, but a feature to be understood. Beyond numbers and models, what does it mean for us to live in a universe that still resists complete description? How should we relate to a cosmos that remains partially mysterious even under intense scrutiny? Somewhere beyond equations, instruments, and debates over decimal places, the universe continues doing what it has always done. It expands. Galaxies drift farther apart. Light stretches as it travels. None of this pauses while we argue about numbers. The cosmos is not waiting for consensus. It unfolds at its own pace, indifferent to whether our models are perfectly aligned. That perspective is important as we arrive here. After all the measurements, the disagreements, the careful scrutiny of methods, and the exploration of new ideas, it is natural to ask what any of this means beyond the technical details. If the universe is expanding a little faster or a little slower than expected, if its history is slightly different from our neat summaries, does that change anything about our place within it? In practical terms, almost nothing changes in daily life. The expansion of the universe does not tug at atoms, pull apart solar systems, or stretch bodies in space. Gravity holds galaxies together locally. Chemistry proceeds as it always has. Time flows at the same pace we experience now. The night sky looks the same to the naked eye as it did generations ago. Yet meaning does not depend on immediacy. The value of understanding cosmic expansion has never been about practical utility. It has been about orientation. Knowing how the universe behaves gives context to everything else. It situates human existence within a much larger story, one that stretches billions of years into the past and quite possibly trillions of years into the future. From that vantage point, the Hubble tension is not a flaw in understanding, but a reminder of scale. We live in a universe vast enough that even measuring its behaviour pushes the limits of knowledge. We infer its properties indirectly, using faint signals that have travelled unimaginable distances. The fact that these inferences mostly agree is remarkable. The fact that they disagree slightly is not shocking. It may even be expected. What matters is how we respond to that disagreement. One response would be to insist on closure, to force the numbers into alignment prematurely, declaring the matter settled. Another response, the one science tends to favour, is patience. Let the data accumulate. Let methods diversify. Allow understanding to mature without rushing it toward a tidy conclusion.